years and years ago, when the company first started with Samurai Siege, we had a very, very basic system where every week we'd show you one promotion, it would pop up, and it would say, great things you can get in the game, $10, one size fits all. And to be honest, it sold pretty well. We thought, this is great, we're selling lots of these. And that game did pretty well. But a couple of years later, when we launched Rival Kingdoms, we came up with a new system, which we're going to talk about tonight, actually, these timeline bundles, where we spent a lot more time setting up different bundles that were aimed at different types of player. And what would happen is the player would play the game, they'd enjoy it, they might see a bundle they want to buy, they'd buy the bundle, and depending on the price of the bundle, that would give us a clue as to the next prices we should show to them to make sure they're getting the bundles that they want to buy. So some guy comes in, spends $5, we know that that's the guy who wants to spend around that amount, and we show bundles on a timeline which was aimed at them. But there's no machine learning involved there, it's all just done through logic. So we have a set of bundles that we have on this timeline, which is aimed at low spenders. If they spend a big amount, they'd get some high numbers, that kind of thing. And there's an obvious next step to this, is like, okay, instead of just having this set rota of bundles, what's next? And the answer was always going to be machine learning. And I think it was a year ago, I stood up here and I had a slide on like, okay, next, machine learning. And it's a year later, we're finally delivering on this promise. And these guys are going to talk about that tonight, about how we're actually going to do it. So without further ado, I'll hand over to Dennis and Atio to tell you more. Thank you.
Cool, thanks Fred. Yeah, so we'll talk about machine learning, some bundles. So yeah, that's us, and this is the whole team. So going from the left, that's Rich, Becky, Dennis, me, and Fred posing very, very awkwardly yesterday because we didn't have a team photo which we could use in this talk. Rich is the only one who's doing a convincing job of not posing. Everyone else is looking very awkward. What we do a bunch of stuff actually. So we've got LTV predictions. This is trying to predict how much a user will spend in our game. This drives millions and millions of spend in ad revenue, and advertising is one of the biggest spends of the company, so it's crucial we get that right. We do live and dev game reporting. We've got 4 games live. We've got 2 games in live alphas, soon to be 3 in beta. So basically, the number of games we operate outnumbers the number of people in our analytics team. So yeah, we're pretty stretched. The point is that we are kind of overworked, and we need to kind of come up with a machine learning system that's going to stay out of our way completely. We want as low maintenance as possible so that we can continue focusing on loads of other things which are very, very important. So very, very easy to train, very easy to develop, very easy to deploy. It was very, very key to us. We also have a real-time and batch process stack. We're massively overstretched, and we are hiring. This is the cursory point where I should say that. So yeah, Fred alluded to this very well. So our brief was to automate timeline bundles in Transformers Earth Wars. It's one of our most successful games. And what a bundle is essentially, as Fred said, you play the game and every once in a while something comes up. And this says, all right, well, would you like to buy some Energon bundle? This is a little bit better value than the kind of things that you can get. And this is what we'd like to seek to automate. There are a bunch of different ones that you can get, different price points, they sell different things, because our customers are very diverse. They've got all sorts of different priorities. Some of them wouldn't be comfortable spending £20 on a bundle, so there are many cheaper ones as well. So how would we go about automating these things? Well, first, how big a slice of the pie is this? Well, these timeline bundles do account for about 35% of our total revenue from this game, at least. So an extra 10% or an extra 5% even would be a meaningful addition to our bottom line. So getting this right could potentially be very profitable. But it's not just about profitability that we're interested in it, because the way it currently works, it's a very, very manual process. So we've got Optimus Prime over here. There we go. Optimus Prime down there, and let's imagine he's a new player in our game, and he starts, and he might serve a certain bundle. This might be a $10 alloy bundle, and he might make his first purchase over here, in which case we'll realize, all right, so he's comfortable spending $10. Maybe he'd want to spend a little bit more. Maybe these ones have a little bit better value, just standard scaling over here. If the higher price points have a little bit better value. So then we move on to this timeline. And all of this is very, very manually curated. We have this complex web involving many different price points and many different bundle compositions. And this is all carefully hand curated, and on top of being hand curated, it gets QA'd by a team. It takes many, many hours to put all this stuff together. And then all of that work goes out of the window when you decide you want to put a new bundle in. You've got to do this whole process from scratch. So what would the dream be? Well, the dream would be you just have a bot. You've got all these bundles over here. When you've got a new one, you just throw it into the mix, and this little bot, it picks out one of these little things, and it decides which ones to serve. So first of all, guiding principle is fairness. This machine learning system is not about trying to find out which users are going to not spend and then give them a better deal. It's not about that at all. It's more like an Amazon recommendation system. It's more about trying to find out, all right, well, you're more likely to want to buy something like this. You are low on this. It's about trying to figure out what users want to buy and then serving that. So ideally, it should make for a better machine learning. It should make for a better user experience, and also it should be better for us as well. So it's about trying to find a solution that works for everyone. So the first thing that most people would think about is using supervised learning. Supervised learning is a dominant paradigm in machine learning at the moment, and the way it kind of works, I like to think of it as a giant interpolation machine. So if you imagine you've got loads of data from all these things, all these points in this area of parameter space, and you needed to and you've got an input over here, and your job is to try to find out the best output, which is over here on the y-axis. Well, you might find all this data, and you might fit a little curve over here. This is the optimal solution for this thing. Then you'd be really good at predicting what the output is given a certain input. In our case, the input is higher dimensional. It's not just a single one number input. It's a multi-dimensional input. So we want like the player state and the bundle type, and then we output the probability that they buy the bundle. But that could work if we were operating in this region of parameter space. And that would work if we wanted to continue serving the timeline bundles. We could probably predict how much money the timeline bundles would make because we've been serving them for a year. But the point is that if we wanted to have a bot to try to choose something optimal, we'd probably have to explore something outside of our data space. So this is some stuff over here we've never really estimated out here. And if we use the supervised learning model, which is this kind of little curve interpolation over here, we'd be completely lost when we came to this new parameter space over here. So we need some kind of way to explore this parameter space. So reinforcement learning, that is the answer to this. So what happens is reinforcement learning is kind of like, it's something called the exploration dilemma. You understand what you've already explored. And so that might be like you've got a kind of solution and it's giving you some Hershey's chocolate, but yeah, they're all right, but they are a bit disappointing. And behind your back, there might be a dairy milk, which would be better. And the only way you realize that there's dairy milk behind your back is if you turn and have a look at it. So this is the whole idea behind reinforcement learning. It's kind of you do what you think is best at any moment. Then you flip a weighted coin with, it's not a 50-50 coin. One side's weighted epsilon, the other side's weighted 1 minus epsilon. That's called an epsilon greedy strategy. You do loads of random stuff, and the more random you are, the more you scope out this parameter space, the more you understand your system. Once you understand your system a little bit better, then you can weight the coin more towards just what you think is the more profitable thing and not towards doing random stuff quite so much. So now I'm going to try to explain a little bit of background in terms of how DeepMind works. I'm going to try to explain DeepMind in one slide. It's probably a little bit ambitious, but if this goes over your head, do tap me on the shoulder afterwards. So essentially, well, DeepMind, what is it? Well, DeepMind made this algorithm that let to play a bunch of Atari games. What was interesting about their work is that they had one algorithm, one architecture, and all it did is look at the raw pixel values of the screen, and it managed to figure out how to play many, many different kinds of game. The way it worked, well, I'll try to explain this equation first. It looks a little bit intimidating, but it's not. What it's saying is, right, each state and each action has a certain quality associated with it. That quality is your immediate reward, and then your future rewards, depending on the state that you move to. It's all that. It's just taking a little step in your little state space, seeing that you get a reward, and then saying, all right, well, my reward is the reward I just got plus the reward I'll get in the future. That one step is all it is. So if we imagine that we've got this little thing, the Atari DeepMind algorithm learned to play this game Breakout quite effectively. And so we figured, well, this is the state we ended with, and we figured, this is a good state. I just got 1 point. That's great. And then working backwards, well, this has got a little bit this state's tightly correlated to this. So even though I didn't get 1 over here, this is a good state to be in. Then you figure out, oh, well, this is also probably a good state to be in, because it leads to getting a point a bit later on. It's essentially how it works. The problem, there are many, many different states that you can have. And so I think DeepMind's contribution was saying, all right, well, what we could do is we could summarize all these states. We can use a convolutional neural network, and that will map similar states to each other. And that was what they did. Our solution is a little bit different to theirs. Our solution is much simpler. Our solution is to get rid of this term that depends on future states and just optimize towards the immediate return. The rationale behind this is that our player states move around a lot. They're very, very random. So what we could do is we could just cross out that state and just optimize on the immediate return. Also, we don't use convolutional neural nets because those are designed about image processing. We just use multi-layer perceptrons. Those are much simpler. I don't have a lot of time because we're going to talk about the motivation, the model, and the stack in half an hour. So I really do urge you guys to come and tap me on the shoulder afterwards if you want to know a little bit more about that. But yeah, so that in essence is the way the model works. It's basically about trying to take DeepMind but make it optimized towards immediate rewards. And yeah, with that out of the way, I'd like to talk to Dennis. I'd like you guys to hear from Dennis about how we actually implemented it.
Thank you, Atib. Hi guys, I'm going to talk to you about the architecture behind our machine learning service and also some of the decisions we've made along the way. So the architecture at the very high level looks like this, and we have the client mobile device, the game service, and also our new machine learning service. And we've intentionally created a new service for machine learning, simply so that the analytics team can start to look after that component because we're experts in that area, and the transformers team behind the game can continue to develop the client and game service and continue to do what they do best, which is build new features into the game and make the game good for our players. So when it comes to the interactions between systems, when the client requests a bundle, it makes a call to the game service. And then the game service reaches out to the machine learning service and it provides a bunch of state about the user, the current state of the user. This is needed so that we can make a recommendation. The machine learning service then returns with the predicted bundle that is to be served to the user, and then the user sees on the device what bundle has been recommended, and they have the choice to either accept that bundle, buy it, or not accept it. And that feedback is routed back to the game service and back to the machine learning service. It's imperative that we have this feedback because later on we'll need the recommendations and the feedback in order to train the model and improve predictions. So if we look at the machine learning service in more details, the components behind it, we're not actually set on the name yet for our machine learning service, but we're actually considering calling it Deep Bundle. I wonder where we got that from. It basically consists of 5 components. We have the REST API, which is our interface to the system. We have our compute, which is like the business logic. The logging, this is probably a bad name for it. It's not so much about logging, it's about data collection. So we want to store all the recommendations that we're making and also the feedback that we receive. And we have our storage persistence layer, which is responsible for holding all of our models, the repository of models, and all the data that we get from our system. And of course, we have training. Now, what's nice about these components is that we can actually map Amazon services directly on top of them. So for the REST API, we'll be using Amazon's API gateway. For compute, we'll be using Lambda. For logging, we're going to be using Kinesis Firehose, and for storage, S3, and for compute, it's going to be EC2. Now, for the benefits of this presentation, we're not going to be talking about the training component, although it's probably very interesting. The reason is because in our architecture, this is a new system for us. Training is not something that we can automate quite easily. We want to make sure that the outputs of the training, the model itself, is producing reliable results. So it's going to be supervised by a human bioanalyst. In this case, it's going to be supervised by Atio. So the model will be trained outside, and the new model will be promoted into production and be live for the game service to consume and use. So a little bit about the services behind these components. So we have API Gateway. This is basically a service which allows you to define RESTful APIs. So you can configure and create endpoints which receive HTTP requests, and then it can trigger Lambda functions. So Lambda essentially is a serverless compute environment which allows you to update or upload functions into that environment and have them executed by an external trigger. So in this case, you would receive a request from API Gateway, and this would trigger a Lambda function. It would invoke our business logic and return a response back to API Gateway. For Firehose, this is essentially a queue in the cloud. And we're using this to collect all the data that's generated by our functions, so the recommendations and also the feedback. And what's nice about Firehose is that it connects with other Amazon services. So what we can actually do is, instead of having to write a consumer ourselves to record information to S3, Firehose can actually record information directly to S3. And S3 is the object storage that we're going to use to store all of our models and all of the feedback. So what's nice about these services is that they have some key benefits. So firstly, they're fully managed. We don't really have time with a small team to start running services and to start running boxes continuously. So it's nice the fact that we can just give this workload to Amazon. They're going to manage the failover, the fault tolerance, the redundancy, the reliability, all the durability stuff, the operations. They're going to do that for us, which is great. They're highly scalable. We don't have to worry about provisioning capacity within our system. The system is going to respond to the workload that's necessary and within the limits of our Amazon account. It's low cost. I think this is probably the best thing about the analytics stack at SpaceApe is that we try to run everything on a really, really small budget. I'm quite proud of that. And from the low cost perspective at Amazon, you pay for what you use. So this is not going to be a high traffic service. It's not going to be something that gets thousands of requests a second. So there's no real need for us to have permanent, persistent infrastructure. So it's great to be able to use and leverage Amazon's Service Compute Cloud basically to lower the cost. And it's serverless, which is trendy. So the machine learning service, Deep Bundle, has two endpoints. It has a recommendations endpoint and a feedback endpoint. I'm going to walk you through both very quickly. So essentially what happens here is when the game service receives a request to retrieve a bundle, it sends a HTTP request, a POST request to API Gateway. What's important here is that we actually get some state from API Gateway. The game service sends some state to API Gateway in the POST request. And it details things like the caste level of the user, the faction they belong to, if they have any builders, Spark, in-game currencies, if they've spent before, those kind of things. And this is all input to the model so that we can make a prediction. So API Gateway forwards its information to Lambda. It triggers a Lambda invocation in the cloud. We're using Python for this. It has a basic structure of a Lambda handler there with two parameters. And the first parameter basically contains the request body that came from the game service. Lambda then will retrieve a model from our model repository. It will evaluate that model, and it will forward not only the request object that came into the system so that we know what's actually happening, it will also record the feedback or the recommended bundle that we're going to make. And that information is sent back to API Gateway. It's put in an envelope, essentially. One of the important things about the response is that it contains a recommendation ID. This is a unique ID that is associated with every recommendation, and it allows us to tie the recommendation to the feedback that we're going to get later. And that response is sent back to the game service and eventually off to the client. So feedback, and Kinesis Firehose will eventually persist the data in S3. So from the feedback point of view, it's a put with the recommendation ID. The game service will tell us whether or not that recommendation has been accepted, i.e. the user has bought the bundle or not. It triggers a Lambda function again. The feedback goes to Kinesis Firehose, and eventually Kinesis will upload that data into S3. I say eventually because although Kinesis is a near real-time stream, it doesn't actually write in near real-time to S3. Basically, you'll get a file up to a maximum every 15 minutes if you configure it that way, or when you reach a certain threshold. In this case, it's 15 minutes for us, or 128 megabytes. We will not accumulate 128 megabytes in 15 minutes, so it's 15 minutes. So why serverless? Well, one of the points about this project is that this is a proof of concept. We have no idea if this is going to be successful or not. So what we didn't want to do was spend a lot of time building complex infrastructure to do this. We want to be quick, very agile, and very simple. So we basically leveraged existing Amazon data blocks. We also have previous experience with all the infrastructure, all the services that I previously mentioned. So we already use S3 for our main data lake. We already have 105 terabytes of data and 15 million objects. For our latest game, Fastlane Road to Revenge, we're using Kinesis Firehose for the collection of the client data, and we've already recorded 7 billion events there. And for Lambda, we've already initiated 3 million invocations in the last 5 months. So the new service is a fraction of what we already do with these services, so it's pretty much small fry. Manpower, as Atty was saying, we are a small team. We're even a smaller team of data engineers, just being me. So I really don't have the time to run these services. So anything I can leverage from Amazon, I'll take it. As I mentioned before, low cost, and it's trendy. So when it comes to machine learning frameworks, We looked at several. We looked at Theano, we looked at TensorFlow, we looked at MXNet. We also looked at Keras, and we looked at Gluon, which are abstractions on top of those, where you can just configure the ML layer underneath. And ultimately, in the end, we decided to go with MXNet. And the reason we went with MXNet was because for actually evaluating a model, for making a prediction, it was twice as fast as TensorFlow. But more importantly, when you write code for Amazon Lambda, you don't just upload the business logic, your Python script. You have to upload all of the libraries that it relies on, and any kind of system libraries as well. And unfortunately, TensorFlow is a huge library. With each release of TensorFlow, it gets bigger and bigger. And Amazon has a hard limit of 500 megabytes for that package. And so the danger is, of course, the next version of TensorFlow is like 490. The next version, all of a sudden, you can't run TensorFlow anymore. So we didn't want to be limited by a potential future problem there. So I hope you guys find some of that information interesting, and I hope you can see how, with a small team, we can do some interesting stuff with machine learning. The next steps are to ship it. So basically, we have all the components done. We need to do some more systems testing, and then it's going to go live into production. And we're going to be doing some A/B testing to make sure that we have the system right. It's going to be targeting a small set of our users first. We'll train the model, we'll try and get some good results out of it, and then we'll either decide to can the project, which I hope we don't, or we'll pivot and try and do something interesting with it. Thank you very much.